Hey guys, we're going to talk about something called a rational function today, which is super important for those of you moving on to calculus. And I know a lot of you actually saw these in Algebra 2, but it's just refreshing our memory on what they look like and what are the important characteristics. So first of all, just what is a rational function? Well, a rational number, guys, is any number that can be written as a fraction. So a rational function is something that can be written in the following form, where maybe your p of x and your q of x are other polynomials, or they could be constants as well. But basically, it's going to look like a fraction. There are two parent functions for these that are pretty important. One of them is just f of x equals 1 over x, and I think it's going to look familiar once I graph it. And the other is f of x equals 1 over x squared. So I'm trying to, let's see, there we go. Trying to drop, there we go, and I'll do another one over here. Oh, not as pretty on that one, but whatever. Okay, so basically what you're looking at is if you started plugging in x values, okay, like if you made a little chart of x's and a chart of y's, what you would notice happening is the further out you go on the x-axis, you're dividing numbers or the number 1 by these really big numbers. And so what it's doing is it's approaching 0. And it's heading towards 0. It's never going to touch it. And what you've learned about that in the past is that those are called asymptotes. So you are going to have a horizontal asymptote and a vertical asymptote as well. And that's just what the parent function looks like. If you want a good point on this, the point 1, 1 and -1, -1, those are good points. Also, you may remember even and odd functions. This is definitely an odd function, this parent function. All right, and now we have the second one. And the only difference between these two is going to be the steepness of the curve, but also the location of these little swooshy parts of the graph. I know that's not very technical, but I think of them as swooshes, okay? We still have our two asymptotes. But now the graph resides in the top two quadrants, and this would be an even function because it has y-axis symmetry. Domain and range on these are interesting because you have to dodge your asymptotes. So the domain is going to be every real number except where the vertical asymptotes are, which in this case is at 0. So you might write it like with interval notation, it would look like this, where you're dodging 0. Range could be the same because you're dodging 0 for your horizontal asymptote. You could also maybe say something where you could just say like y cannot equal 0. That would be an acceptable range as well, where you're saying that that's where that asymptote exists. Okay, so moving on to characteristics of rational functions. So we need to talk about this because they're not all going to be parent functions, and they're not all going to be transformations of the parent function. They could be, but they're not always going to be. And I didn't even put that part in the notes, but for those of you that care, in fact, I'll come back here real quick. For those of you that care, if you did want to just do transformations to the parent function, this is pretty much what it would look like. You could have a vertical stretch or shrink show up in the numerator. You could have a left or right movement show up in the denominator, and you could have your vertical translation show up at the backside. So those are a few things that could happen if you wanted to do some shifting of these parents without, having to do too much thinking. Just left, right, up, down, and then stretch or shrink. Okay, what if they're more complicated? Well, the graphs could have the following properties. You could have a hole in the graph. You potentially have x-intercepts. You might not, but you could. You potentially have a y-intercept. Usually we do have a y-intercept on these. You could have vertical asymptotes, as we saw above. And then you could have horizontal asymptotes. Now, I'm not going to write horizontal asymptotes. What I'm going to do is call it an end behavior asymptote, because it could be horizontal, okay? Just like the parent functions, or these things could also be slants, what we call a slant asymptote. So I'm going to write the notes here really fast on how to find everything, and then we'll do some examples. Okay, a hole exists on a rational function if a factor cancels in the numerator and denominator. So basically, if there's a common factor, all right, on the top and the bottom. And that doesn't happen every time, but sometimes it does. And if it does, it creates a hole in the graph. The x-intercepts can be found by setting the numerator to 0. You're actually setting the entire function to 0, but the numerator, if the numerator is 0, guys, on a fraction, then the whole thing has to turn into 0. So setting the function or the numerator equal to 0, and then you would just solve, okay? The y-intercept is setting all x's to 0 and simplifying. So you're basically just like plugging in 0 for every single x and then see what happens. The vertical asymptotes are going to be the numbers that make the denominator 0. And the reason for that is these are fractions, right? So if you have a number over 0, this is bad, right? This is what we've called the undefined all school year. So that is what basically a vertical asymptote is, a graphical representation of this situation over here, a number over 0. Okay, and then the end behavior asymptote's a little trickier. You have a couple of things that can happen. What you want to do is you want to check the exponent behavior in the numerator, in the denominator. Numerator over denominator, and you want to see where your largest exponent exists, and that's going to sort of largest exponent exists, because what that's going to do is it's going to tell you what's going to happen to your function. I hope you guys can read my writing. It's really terrible. I'm sorry. Having to write vertically here on my screen. Okay, so there's 3 rules. All right, 1, 2, 3. So the first thing is if we're comparing exponents and we're looking at the top and we're looking at the bottom, there is potential for there to be a larger exponent on the bottom, aka denominator, right? And if you have a higher power on the bottom, then you are always going to have a horizontal asymptote on the axis. So y equals 0 will always be that asymptote, just like the parent functions above, okay? Now, if the exponents match, if the powers match from the top to the bottom, okay, then all that you need to do is look at those leading coefficients. And they are going to make your horizontal asymptote. So it'll still be a horizontal asymptote. It'll just be at some rando number. We'll see an example of this in just a second. And then case number 3 is if the problem has a larger exponent on the top. And this is actually the most interesting graph, but it's also the crappiest one to have to get through, because if this happens, guys, you are most likely going to be doing long division of polynomials, or synthetic division, if you remember synthetic division. But you're going to have to do division of polynomials, and then you are going to have a slant asymptote. All right, so those are the 3 things that can happen. So hopefully you have these notes written down. If not, hit pause and write them down, because I'm not going to come back up to this, but we're going to do an example, and I'm going to roll through every single one of these to show you how to do a problem. In fact, we'll probably do 2 problems. All right, so let me switch colors here. All right, so the first one that we'll do for examples, let's do this one here. How about 2x minus 5 over x squared minus 9. All right, so what you want to do is every time you see a polynomial, a rational function, you want to try to simplify first. And what that means is basically factor it if possible, because if there's a common factor, you're going to look for the whole first, okay? So we're going to look for the whole if there is one. So when I factor this, now the numerator does not factor, so I'm just going to recopy it, and the denominator does factor to x plus 3 and x minus 3, but notice that nothing is canceling out from the top to the bottom. So since there's no common factor, then I know that there are no holes in this graph. And then I'm going to move to the second thing, which above the second thing I wrote was to look for my x-intercepts. So looking for x-intercepts, you are setting this problem equal to 0. And you really only have to worry about the numerator, because when the numerator is 0, the entire problem is 0. So let's just solve this out, right? So I'd move the 5 over, divide by 2. So my x-intercept is going to be at the point, notice I'm writing it as a coordinate, 5/2, comma 0. So I know I have a x-intercept there. Number 3 above was the y-intercept, and you're going to find that by plugging in 0 for every x in the problem. All right, and you can plug it into the original, you can plug it into the factored form, it really doesn't matter, but I'm getting -5 over -9, which is just 5/9, right? So if this is a y-intercept, then I'm going to write it as 0, 5/9. So now I have 2 good points on my graph, okay? So now let's start looking for asymptotes. All right, so number 4, what did I do above for number 4? I think that was vertical asymptotes. So vertical asymptotes is where you set your denominator equal to 0. Now, I have already factored my denominator in that step above, so I'm setting these factors equal to 0, which means when I set each parenthesis equal to 0, I'm getting the following 2 values. So guys, that does mean, yes, there are 2 vertical asymptotes that can happen on a graph, okay? And then number 4 is to check for the end behavior asymptote. So the end behavior asymptote, what it says above is to compare the powers, right? Compare the exponents. So if I come up here and I look at my largest term on top and my largest exponent on the bottom, this one is what I would consider bottom heavy, meaning it has a bigger exponent on the bottom. And that's one of the cases we wrote down that if it is bigger on the bottom, then it's going to be like the parent function, and it's always just going to approach 0. It's just a rule to memorize. Bigger on bottom, it's always going to be 0. So now that we have these things, I'm going to shrink this down just a little, and let's try to sketch a very quick graph. All right. So there we go. Okay, so what I'll do, I'll switch colors to make it a little easier. Let me just graph what I know. There's no holes. I have an x-intercept at 5/2, which is the same as 2.5, right? So 2.5, comma 0, I have an x-intercept. Y-intercept at 0, 5/9. Okay, so 5/9 is just a little bit between 1/2 and 1, so it's just somewhere in here. We'll put a point. And then I have, let's see, I have 2 vertical asymptotes. One of them is at 3. One of them is at -3. And then I have a horizontal asymptote on the, the axis. Oh no, hold on one second. There she is, okay. Oh man, it didn't like my asymptotes. 1, 2, 3. 1, 2, 3. Okay, cool. Now, something you'll need to understand is that on this graph, this quadrant is now cut up into 3 pieces. So what I'm trying to say is that there is something that's going to happen over here, there's something that's going to happen in the middle, and there's something that's going to happen there. So you need to figure out what's going to happen on all sides of your asymptotes, okay? So to do that, you have a couple of options. I'm a big fan of just a really small T-chart where I just sort of pick a few points just to see what's happening. Now, I already know in the middle, if I just start playing connect the dots and I connect this one to this one, it just feels like I should keep going down. And beyond this, I feel like I would then hit this wall and I would go up. Now, how do I know that I would go up and not down? Well, it can't go back down, guys, because then it would have hit the x-axis again, and that answer would have shown up over here, but it didn't, so you can't go back down. Now, if you don't trust that, then pick a value like -2 for your x, and just plug it into the original function and see what the y is. And then you can see exactly where it's going to go. Now, I need to see where I need to go on all sides. So let's see. Here's, if that asymptote is at 3, I'm going to pick 4, and I think I'm going to pick -4 and just see what's happening. So if, and the reason I'm choosing those is because they're outside of the asymptotes, and I just want to see what the graph's going to do. So if I pick 4 and plug it into the original function, 4 squared, okay, I've got 8 minus 5 is 3 over 16 minus 9, which is 7. I think I did that right. Yes, so 3/7. So I'm getting, when I plug in a 4, if I go over 4, I'm getting 3/7, which is just right there. You know, it's just a little bit above. When I plug in -4, let's switch these to negatives now. Okay, that would be still a 7 on the bottom, but then it would be like -13 on the top. So -4 is going to go to a -13/7, which is just almost -2. So the cool thing is that once you get these points, some of y'all will be scared to guess, and if you're scared to guess, then just pick another point and plug it in. I feel really confident that this graph is going to look like this, and the reason I know that is because above, remember above we had drawn the parent function, and these swooshes on the parent function, this is what they usually look like, and they usually alternate in the quadrants. So I feel really good, but you could go type it in a calculator or make a few more points down here if you want to get like more precise. Okay, so now we'll make up another one. Let's make up one. I'm going to try to make one that has a hole. Okay, so how about this one here? So how about y equals okay, so let's say that this was our problem. Then what we would do is just like before, step number 1, let's start with simplifying this, which means factoring it, and let's just see what happens, okay? So if I factor the numerator, I get x plus 5 times x minus 5. That's a difference of squares. And then on the bottom, let's see, two numbers that multiply to 10 but add to -7. So how about x minus 5 and x minus 2? Would that work? See, if we FOIL that out, that would work. All right, now notice right now I have these two factors that are common, aka they reduce. All right, you can get rid of them. So if you have a common factor that reduces, that common factor is going to help you create the hole. Now, the way you're going to find exactly where the hole is you're just going to set the common factor that you just crossed out, you're going to set it equal to 0. And so I know that the x part of the coordinate is 5. Like if I just solve this out, I get x is 5. So now all you have to do is take that 5 that we just found and plug it back in to this function. Okay, to the leftovers of this function, because guys, once you cross out the common factor, the thing that's left, okay, this thing that's left, this is your new problem. You should only deal with what is in the box right now, and that's not just for this part, but it's for like literally everything else that we're going to do. Please use the reduced form for the rest of this problem. So I'm going to take this 5 and plug it in here, and I'll get a 10 over 3. So there's going to be a hole at 10/3, or the point 5 comma 10/3. So when I go to graph that later, I need to keep that in mind. Okay. Moving back to the rest of the lineup. Number 2, x-intercepts. You're going to set your new numerator equal to 0. And you're going to get the x-intercept of -5, 0. Number 3, we're going to do our y-intercept. So that's where we plug in 0 for all remaining x's. So 0 plus 5 over 0 minus 2. So my y-intercept is at 0, -5 halves. Number 4 is vertical asymptotes. So I'm going to take my new denominator, set that equal to 0, and I have a vertical asymptote at x equals 2. And then lastly is my end behavior asymptote. So if I look above and I compare x plus 5 over x minus 2, the exponents match from the top to the bottom. And if you go look at the different things that can happen, that's one of the choices. If the powers match, you just reduce the leading coefficient. So in other words, x over x reduces to 1. So that is where the horizontal asymptote is going to be. Now we graph. So, okay. All right, so we have, let's start with the whole. The whole is at the point 5, 1, 2, 3, 4, 5, 10 thirds. So 10 thirds is a little over 3. 5, 10 thirds. So somewhere about right there. Now that's a whole. I don't know why I drew it as a closed circle. That should be an open circle right there. There we go. I have an x-intercept at -5. 1, 2, 3, 4, 5. So that's a solid circle. I have a y-intercept at -5 halves, which is -2.5. And then an asymptote at 2, x equals 2. And a y asymptote, a horizontal asymptote at y equals 1. All right, and now I'm just going to fill in what this graph looks like. Now, I'm actually not even going to make a t-chart on this one, only because I've drawn enough of these in my life and I know what the parent function looks like, and I feel super confident just playing connect the dots. If you do not feel confident playing connect the dots, pick a number over here, like 3 or 4 or 6 or 7, and plug it in, remember, to the new one. Plug it in right there and get its y, and then you'll know what it's going to do. But I'm telling you right now, that's what it's going to do. It's going to be one of those swishy things, but you've got that big open circle. You've got the hole that you need to make sure stays a hole, okay? All right, so that is a long enough video for now. If you want to go look up online slant asymptotes, I mean, literally you could just go Google that. It's pretty much if the top power is bigger than the bottom, you can expect to see a diagonal asymptote show up in your picture. And I'll put another video up maybe that I like from somebody else that demonstrates that. But most of your graphs are going to deal with what you saw here today. Thank you.